December 1944. Kaiser Wilhelm Institute, Berlin-Dahlem. Professor Werner Heisenberg, Nobel laureate and director of Germany's uranium project, stared at calculations that refused to yield the numbers he needed. His team had spent 5 years pursuing atomic fission, maintaining confidence through scientific excellence and institutional prestige. Yet American scientists, dismissed by German physicists as theoretically unsophisticated and technologically backward, were solving problems German science considered insurmountable. The Americans were building something enormous. What Heisenberg didn't understand was that 5,000 miles away in Los Alamos, New Mexico, a city of scientists that didn't officially exist, was constructing atomic weapons using industrial methods German physics considered impossible. The American scientific apparatus, operating with resources German researchers couldn't imagine, had achieved what German theoretical physics said required decades: practical atomic weaponry. Within months, German physicists would watch their research facilities captured. Within a year, they would learn about Hiroshima. Within decades, they would understand they'd been pursuing the right physics with completely wrong methods while fighting a scientific war they never knew they'd lost. The confidence of excellence. Germany's confidence in their atomic research superiority stemmed from legitimate scientific dominance. German physics had won more Nobel Prizes than any nation. German theoretical work had discovered nuclear fission itself. German experimental apparatus was the finest in Europe. German scientific institutions possessed century-old traditions of rigorous research. Otto Hahn and Fritz Strassmann had discovered nuclear fission at Kaiser Wilhelm Institute in December 1938. Lise Meitner and Otto Frisch had provided the theoretical explanation in 1939. German physicists understood atomic energy before anyone else. They had the physics. They had the scientists. They assumed they had the lead. Werner Heisenberg, appointed to lead Germany's uranium project in 1939, was arguably the world's most accomplished theoretical physicist under age 50. His uncertainty principle had revolutionized quantum mechanics. His theoretical work was studied worldwide. The Reich entrusted atomic research to Germany's finest scientific mind. Professor Kurt Diebner, physicist at Army Ordnance Research, wrote in June 1940, "German theoretical physics leads the world. We discovered fission. We understand the principles. We possess Europe's finest experimental facilities. American physics is competent but lacks our theoretical depth and institutional excellence. The British focus on radar and conventional weapons. We have years to develop atomic weapons before others can compete." This assessment was reasonable in 1940. German physics did lead theoretical understanding. German facilities were excellent. German scientists were world-class. What Diebner couldn't know was that theoretical excellence meant nothing against American industrial organization. Meanwhile, in Japan, a parallel research program operated under even greater delusions about atomic feasibility and timeline. Japan's parallel ambition. April 1941, Imperial Japanese Army Technical Research Center, Tokyo. Lieutenant General Takeo Yasuda approved funding for NIGO project, Japan's atomic bomb program under physicist Yoshio Nishina. The project would investigate military applications of atomic fission, recently discovered and publicized by German physicists. Nishina, Japan's leading nuclear physicist, had studied under Niels Bohr in Copenhagen and understood atomic theory thoroughly. He'd built Japan's first cyclotron, a particle accelerator for nuclear research. He possessed the theoretical knowledge and experimental capability to pursue atomic weapons. But Nishina faced obstacles that made German challenges look trivial. Japan's industrial capacity was a fraction of Germany's. Japan's access to uranium was limited. Japan's electronics manufacturing lagged Western standards. Japan's mathematical computing capability was primitive. Most critically, Japan's scientific community was tiny compared to American or German physics establishments. Professor Bunsaku Arakatsu, leading Kyoto University's parallel F-GO atomic program, for the Imperial Japanese Navy, reported in September 1942, atomic weapons are theoretically possible, but practically distant. Uranium enrichment requires industrial capability we lack. Theoretical understanding is insufficient without manufacturing capacity. American industrial advantage is significant, but we estimate atomic weapons require at least 10 years development. This timeline provides strategic advantage to patient powers. Arikatsu is catastrophically wrong about American timelines. American physics wasn't patient. It was systematic, industrial, and faster than Japanese planners imagined possible. The German approach: theory over engineering. German atomic research proceeded along paths that seemed scientifically rigorous, but were strategically disastrous. Heisenberg's team focused on reactor development using natural uranium and heavy water as a neutron moderator. This approach was theoretically sound but practically difficult. Heavy water production required enormous industrial facilities. Natural uranium in sufficient quantities was increasingly difficult to obtain as Allied forces captured German-controlled territories. The German research program was organized around existing institutional structures. Kaiser Wilhelm Institute handled theoretical work. Army Ordnance managed practical applications. University laboratories conducted specialized experiments. This distribution of effort seemed efficient, but created coordination problems and prevented concentrated resource allocation. Professor Walter Botha, experimental physicist, built Germany's most sophisticated radiation measurement equipment. His measurements in 1941 suggested that graphite, an alternative to heavy water as a moderator, would not work for German reactor designs. This conclusion was correct, given his experimental conditions, but missed that ultra-pure graphite, manufactured with better industrial processes, would work excellently. American researchers discovered that ultra-pure graphite worked perfectly. German researchers concluded graphite was unsuitable. This single experimental difference shaped divergent research paths that ultimately determined success or failure. By 1943, German atomic research had achieved laboratory-scale nuclear reactions, but no path to weapons-grade materials. Their heavy water reactor approach required the Vemork plant in Norway, which British commandos sabotaged repeatedly. Their alternative approaches required industrial resources Germany increasingly couldn't spare. The Japanese struggle: ambition without resources. Japanese atomic research faced even more fundamental obstacles than German programs. Nishina's NIGO project required uranium enrichment to produce weapons-grade material. Thermal diffusion, the method his team pursued, required enormous electrical power. Japan's electrical generation capacity was limited and increasingly targeted by American bombing. Japan's largest cyclotron, built by Nishina, could produce trace amounts of enriched uranium for experimental purposes. Scaling this to weapons-grade quantities required cyclotrons hundreds of times larger. Japan's industrial capacity couldn't build them. Japan's copper reserves couldn't supply the electromagnetic coils. Japan's electrical grid couldn't power them. Lieutenant Colonel Tatsusaburo Suzuki, Army liaison to NIGO project, reported in January 1944. Current progress is scientifically interesting, but militarily irrelevant. Uranium enrichment at required scales demands industrial capabilities we do not possess and cannot develop under wartime constraints. Atomic weapons are theoretically achievable, but practically impossible with available resources. Recommend project continuation for research purposes only, not operational weapons development. His recommendation acknowledged reality, but arrived too late. Japan had already invested significant resources in research that would never produce weapons. Meanwhile, American scientists were months away from testing a functional atomic bomb. The American secret: industrial science. What German and Japanese physicists never understood was that American atomic research wasn't primarily a physics problem. Americans treated it as an engineering and manufacturing challenge. The Manhattan Project, authorized in August 1942, operated on scales German and Japanese scientists couldn't conceive. The project budget exceeded $2 billion, more than the entire Japanese military research budget. The project employed 130,000 personnel at peak, more than Germany's entire scientific research establishment. Most critically, Americans weren't trying to perfect the science before building. They were building at scale while perfecting the science simultaneously. J. Robert Oppenheimer, scientific director at Los Alamos, assembled an unprecedented team. The laboratory included Nobel laureates from multiple disciplines, working on specific technical problems, theoretical physicists calculating critical mass and explosive yields, experimental physicists testing materials and reactions, chemists developing plutonium separation techniques, metallurgists working with materials that had never been purified before, engineers designing mechanisms for weapons nobody had built, mathematicians calculating neutron diffusion without computers adequate for the complexity. But Los Alamos was just the scientific center. The real American advantage was industrial scale. Oak Ridge, Tennessee, housed uranium enrichment facilities that dwarfed anything Germans or Japanese imagined. Calutrons, electromagnetic separators using cyclotron principles, filled buildings the size of aircraft factories. Gaseous diffusion plants processed uranium through thousands of stages. Thermal diffusion columns stretched stories high. The K-25 gaseous diffusion plant at Oak Ridge covered 44 acres under one roof. It was the largest building in the world when constructed. It consumed electricity equal to a medium-sized city. A single American enrichment facility was larger than Germany's entire atomic research infrastructure. Hanford, Washington, housed plutonium production reactors that eclipsed all German reactor research. The B reactor, operational by September 1944, was producing weapons-grade plutonium months before German physicists achieved sustained nuclear reactions at laboratory scale. General Leslie Groves, military director of the Manhattan Project, approached atomic weapons as a production problem, not a research problem. His background in military construction, including building the Pentagon, gave him perspective that pure scientists lacked. He understood that theoretical possibility meant nothing without industrial capability to manufacture at scale. German scientists' growing doubts. By late 1943, some German physicists suspected they'd lost the atomic race before fully joining it. Heisenberg traveled to Copenhagen in September 1941 to meet Niels Bohr, his former mentor. The meeting's details remain controversial, but evidence suggests Heisenberg was probing whether American and British scientists were pursuing atomic weapons seriously. Bohr's carefully neutral responses revealed nothing, but Heisenberg left concerned that Allied research might be further advanced than German intelligence suggested. Professor Carl Friedrich von Weizsäcker, Heisenberg's theoretical collaborator, wrote in his diary in December 1943, "Our research proceeds scientifically but advances slowly. Reactor development requires resources increasingly diverted to conventional weapons. If Americans are pursuing atomic weapons with their typical industrial intensity, they may achieve in years what we assumed required decades. German theoretical superiority means nothing if Americans can brute force solutions through sheer resource application." Von Weizsäcker understood the strategic situation better than most German physicists. Science wasn't the bottleneck. Industrial capacity was. And Germany's industrial capacity was stretched to breaking, while America's industrial capacity seemed unlimited. German physicist Erich Bagge, working on isotope separation, visited production facilities in 1944 and reported, "Our theoretical approaches are sound, but practical implementation requires manufacturing capability we lack. American industrial capacity exceeds ours by factors we cannot overcome through scientific excellence alone. If they are building atomic weapons, they can outbuild us, regardless of theoretical sophistication." His superiors dismissed the concern. German scientific pride couldn't accept that American engineering might overcome theoretical German advantages. Japanese scientists' impossible task. Japanese physicists faced reality earlier than their German counterparts because their limitations were more obvious. In March 1943, American B-29 bombers began systematic destruction of Japanese industrial capacity. Nishina's cyclotron research facility wasn't specifically targeted, but electrical generation capacity serving Tokyo was. Power outages forced suspension of enrichment experiments, requiring constant electrical supply. Professor Arakatsu at Kyoto reported in June 1944, uranium enrichment research continues, but practical weapons development is impossible under current conditions. American bombing systematically destroys industrial capacity needed for any large-scale atomic project. Even if we solve technical problems, we lack resources to implement solutions. Recommend research continuation for post-war scientific purposes only. Japanese Navy Command still hoped atomic weapons might provide desperate strategic advantage. They allocated additional funding to FGO project in August 1944, but resources couldn't change physics or create industrial capacity that no longer existed. Lieutenant General Yasuda reviewed NIGO progress in November 1944 and confronted uncomfortable truth. 5 years of research has produced scientific understanding, but no practical path to weapons. German atomic research reportedly faces similar challenges. American silence on atomic matters suggests either they have abandoned research or succeeded beyond our expectations. Their silence worries me more than their propaganda would. His instincts were correct. American silence meant operational security around the world's most secret military program, not abandonment of research. The scale they never imagined. If German or Japanese scientists had learned the Manhattan Project's true scale, they wouldn't have believed it. Oak Ridge alone employed 75,000 workers at peak. The site consumed 1/7 of all electrical power in the United States. The Y-12 electromagnetic separation facility cost $477 million, more than Japan spent on all military research during the entire war. Hanford employed 50,000 construction workers, building plutonium production facilities. The site covered 586 square miles, larger than Los Angeles. 3 plutonium production reactors operated simultaneously, each larger than any German experimental reactor. Los Alamos housed 6,000 personnel in a secret city that officially didn't exist. Scientists worked in facilities that matched or exceeded the best European laboratories. Computing resources included IBM punch card machines, programmed for complex calculations German mathematicians did by hand. The Manhattan Project spent more money developing the gaseous diffusion process alone than Germany spent on all atomic research. The project consumed more electricity in 1945 than most medium-sized countries. The project employed more scientists than German and Japanese atomic programs combined by factors of 10. Professor Philip Morrison, Manhattan Project physicist, later recalled, "We knew German physics was excellent. We knew Japanese scientists understood the theory. What we didn't think they knew was the sheer industrial scale required. We weren't doing better physics. We were doing physics at such enormous scale that incremental improvements became revolutionary capabilities." German capture and disbelief. April 23, 1945. Allied forces captured the German atomic research facility at Haigerloch, where Heisenberg's team had been conducting final reactor experiments. American scientific intelligence officers, part of the Alsos mission, examined the German reactor and expressed surprise at its primitive scale. The reactor consisted of uranium cubes suspended in heavy water inside a concrete pit. It was scientifically sophisticated, but industrially insignificant. A laboratory experiment, not a path to weapons. Colonel Boris Pasch, military commander of the Alsos mission, reported, "German atomic research is years behind Manhattan Project. They have achieved laboratory-scale reactions, but possess no enrichment capability, no plutonium production, no weapons design. Their scientists are excellent, but their program is essentially pre-industrial. Samuel Gaudsmit, scientific director of Alsos mission, interviewed captured German physicists and concluded they'd never understood the industrial requirements for atomic weapons. They'd been pursuing perfect science, while Americans pursued adequate engineering at massive scale. Heisenberg and 9 other German physicists were interned at Farmhall, England, where British intelligence secretly recorded their conversations. The transcripts reveal German scientists who understood atomic theory perfectly but couldn't comprehend American industrial achievement. When news of Hiroshima reached Farmhall on August 6, 1945, German physicists initially believed the reports were propaganda. Heisenberg calculated that atomic weapons required uranium enrichment or plutonium production at scales they considered impossible with 1945 technology. Otto Hahn, discoverer of fission, expressed disbelief. They can't have atomic weapons. The enrichment required is impossible. We calculated the requirements. The industrial scale is absurd. Heisenberg reviewed American announcements about the bomb and slowly accepted reality. If they did it, they didn't do it through better physics. They did it through better engineering. They built at scales we never imagined. They succeeded not because they understood fission better than we did. They didn't. They succeeded because they built bigger. Much, much bigger. Japanese scientists learned the truth. In Tokyo, Professor Nishina listened to radio reports of Hiroshima and understood immediately what had happened. He'd spent 5 years pursuing atomic weapons with insufficient resources. He'd known the theory. He'd understood the requirements. He'd recognized that Japan lacked industrial capacity for weapons-grade production. Now Americans had demonstrated they possessed that capacity in abundance. Nishina gathered his research team on August 7, 1945, and delivered an impromptu lecture on what Hiroshima meant. The Americans achieved what we knew was theoretically possible but practically impossible for us. They succeeded not through superior physics, our theoretical understanding equals theirs, but through industrial capacity we cannot match. An atomic bomb requires enriched uranium or plutonium in quantities demanding industrial facilities we never possessed. They built those facilities while fighting wars on 2 continents. Their industrial capacity exceeds our estimates by factors we didn't think possible. Professor Arakatsu in Kyoto reached similar conclusions independently. He calculated that producing Hiroshima's estimated yield required uranium enrichment or plutonium production at scales Japan couldn't have achieved in decades even without wartime disruptions. Lieutenant General Yasuda, reviewing NIGO project files after Hiroshima, wrote in his final report, "Japanese atomic research pursued correct theoretical approaches, but never possessed resources for practical implementation. American success demonstrates that modern weapons development requires industrial capacity, not just scientific knowledge. Japan's scientific community understood atomic physics adequately. Japan's industrial base could never have translated that understanding into weapons. The Americans possessed both knowledge and capacity. We possessed only knowledge." His report acknowledged what German physicists were simultaneously realizing. Theoretical sophistication without industrial capacity was militarily worthless. Nagasaki and the second design. When Americans dropped a second atomic bomb on Nagasaki on August 9, 1945, surviving Axis scientists realized the implications were even more devastating than they'd initially understood. Hiroshima used a uranium bomb. Nagasaki used a plutonium bomb. Americans hadn't just built one type of atomic weapon. They'd built 2 entirely different designs, both functional, both produced in quantities sufficient for operational use. Heisenberg at Farmhall analyzed reports of the second bombing and explained to his fellow internees, 2 different bomb types means they didn't barely succeed. They succeeded overwhelmingly. They have uranium enrichment facilities producing weapons-grade material. They have plutonium production reactors breeding weapons-grade plutonium. They have weapons laboratories designing multiple bomb types. They have industrial capacity to produce atomic weapons as if they were conventional munitions. We weren't just behind. We were never in the race. Carl Friedrich von Weizsäcker added, they treated atomic weapons as a production problem, not a research problem. While we perfected theory and built laboratory experiments, they built factories. While we calculated precise requirements, they built excessive capacity. While we aimed for scientific excellence, they aimed for industrial sufficiency. They won because sufficiency at scale defeats excellence at laboratory scale. In Japan, Nishina reached identical conclusions. He'd spent the war believing atomic weapons were decades away from practical deployment. Americans had deployed them in 1945, 6 years after fission's discovery. The timeline compression was staggering. The methodological divide. Post-war analysis revealed that German, Japanese, and American scientists understood atomic physics comparably well. What differed catastrophically was methodology. German atomic research followed traditional European scientific traditions: careful experimentation, theoretical perfection, institutional collaboration, and cautious resource allocation. This approach produced excellent science but slow progress toward practical applications. Japanese atomic research followed similar patterns, but with fewer resources and more desperate timelines. Japanese scientists understood what they needed but never possessed means to achieve it. American atomic research abandoned traditional scientific methods in favor of industrial production techniques. Parallel research paths exploring multiple approaches simultaneously. Massive resource allocation accepting inefficiency for speed. Industrial-scale facilities built before research proved exact requirements. Compartmentalized organization preventing coordination delays. Production focus treating atomic weapons as manufacturable products. General Groves explicitly rejected efficient resource allocation in favor of parallel development. When scientists debated whether electromagnetic separation, gaseous diffusion, or thermal diffusion would work best for uranium enrichment, Groves built all three at full industrial scale simultaneously. This was scientifically inefficient but strategically brilliant. At least one method would work, and speed mattered more than efficiency. Professor Ernest Lawrence, inventor of the cyclotron and designer of electromagnetic separation facilities, later explained, "We didn't know which method would work best, so we built them all at production scale. Germans would have perfected one method before building. We built first, perfected during operation. Scientifically wasteful, strategically decisive." Los Alamos researchers pursued multiple bomb designs concurrently. The gun-type uranium bomb, Little Boy, and implosion-type plutonium bomb, Fat Man, represented entirely different approaches. Americans developed both in parallel. Germans would have perfected one design before attempting another. This parallel development philosophy extended throughout the Manhattan Project. Multiple reactor designs, multiple enrichment cascades, multiple weapons configurations, multiple delivery mechanisms. The approach guaranteed success somewhere while ensuring massive resource expenditure everywhere. The mathematics of scale. When precise figures emerged after the war, Axis scientists confronted the mathematical impossibility of competing with American industrial investment. The Manhattan Project cost $2 billion, 1945 dollars, equivalent to approximately $30 billion in 2025 terms. This exceeded Germany's entire military research budget across all fields during the entire war. Oak Ridge's K-25 gaseous diffusion plant alone cost more than Japan spent on all scientific research during the war period. A single building in Tennessee represented greater industrial investment than the entire Japanese scientific establishment. Hanford's plutonium production represented chemical engineering at scales German chemists considered impossible. Each Hanford reactor produced plutonium through irradiating tons of uranium, then extracting plutonium through chemical separation processes, handling radioactivity levels that would have shut down any German facility. The B reactor at Hanford generated 250 megawatts thermal power. Germany's largest experimental reactor, the B8 at Heigerloch, generated essentially zero power. It barely achieved critical reaction. The scale difference wasn't incremental, it was categorical. Professor Otto Hahn calculated after the war that duplicating Manhattan Project infrastructure would have required diverting Germany's entire aluminum production, one-third of electrical generation, and most chemical manufacturing capacity for 3 years. This was obviously impossible while fighting a two-front war. Japan's situation was even more impossible. Japanese industrial capacity never exceeded 10% of American capacity. Even allocating Japan's entire industrial output to atomic weapons wouldn't have matched Manhattan Project resources. Why German physics failed. German physicists spent decades after the war debating why they failed to build atomic weapons. The debates revealed fundamental misunderstandings about what had actually occurred. Some German scientists claimed they'd deliberately sabotaged atomic research because they didn't want Hitler to possess atomic weapons. Post-war evidence thoroughly disproved this claim. German scientists had pursued atomic weapons seriously. They'd simply failed to achieve them. Some claimed they'd focused on reactors for power generation rather than weapons. Evidence showed they'd pursued weapons, but concluded weapons required resources Germany lacked. Some claimed they'd made crucial theoretical errors that set them back years. Detailed reviews showed German theoretical work was essentially correct. Their engineering approaches were simply too limited in scale. The truth was simpler and more brutal. German atomic research failed because Germany lacked industrial capacity to build atomic weapons while fighting a two-front war. Even Germany's peacetime industrial capacity would have been insufficient to match American wartime atomic investment. Heisenberg later wrote, "We didn't fail because we didn't understand the physics. We failed because we didn't understand that physics was insufficient. Atomic weapons required industrial capacity we didn't possess. Better theoretical understanding wouldn't have changed this. We needed factories, not formulas. America had both. We had only formulas." Professor Max von Laue, Nobel laureate and German physics elder statesman, provided the most honest assessment. "We believed scientific excellence would overcome industrial disadvantage. We believed German theoretical superiority would defeat American industrial capacity. We were wrong. Modern warfare is industrial warfare. Superior science without superior industry loses to adequate science with superior industry. Americans didn't need to be better physicists. They needed to be, and were, better engineers and manufacturers." Why Japanese physics never had a chance. Japanese atomic research failed even more completely than German efforts because Japanese scientists understood their limitations earlier, but couldn't convince military leadership to abandon impossible objectives. Nishina knew by 1943 that practical atomic weapons exceeded Japanese industrial capacity. He continued research hoping for theoretical breakthroughs that might reduce industrial requirements. No such breakthroughs occurred because they couldn't. The physics was fixed, and the industrial requirements were non-negotiable. Professor Arakatsu explicitly told Navy Command in 1944 that atomic weapons were impossible with available resources. Navy leadership ordered research continuation anyway, hoping American bombing might somehow spare atomic facilities while destroying everything else. It didn't. Japanese scientists weren't wrong about physics. They were realistic about capabilities. They understood that knowing how to build atomic weapons meant nothing without capacity to actually build them. Nishina later reflected, "We pursued atomic weapons, knowing we couldn't build them because military leadership demanded we try. Scientific honor required honest assessment of impossibility. Military honor required attempting anyway. We failed as we knew we must, but failure was honorable acknowledgement of reality, rather than shameful inability. We understood the physics, we lacked the factories." The post-war reckoning. When German scientists were finally released from internment and returned to Germany in January 1946, they found a nation devastated and a scientific community scattered. Many leading German physicists had fled to America before the war. Those who remained faced a shattered infrastructure and international distrust. Heisenberg, von Laue, Hahn, and other farm hall detainees attempted to rebuild German physics under Allied occupation. But Germany's physics community, which had led the world for generations, would never regain its pre-war dominance. Too many scientists had emigrated. Too much infrastructure was destroyed. Too much trust was lost. German scientists grappled with the question of their responsibility. Had they failed Germany by not building atomic weapons? Or had they served humanity by failing? Post-war debates often framed German atomic failure as deliberate moral choice, rather than acknowledging simpler truth. They failed because they couldn't succeed, regardless of moral considerations. In Japan, Nishina attempted to rebuild Japanese physics research after surrender. American occupation forces initially ordered destruction of all cyclotrons, fearing Japanese atomic research might resume. Nishina's cyclotron, product of years of work, and Japan's finest scientific instrument, was destroyed in November 1945. Nishina later recalled watching American soldiers dismantle his life's work. They feared we might resume atomic weapons research. They didn't understand we'd never had capability to begin such research meaningfully. They destroyed our cyclotron not because it was dangerous, but because they didn't realize how primitive it was compared to their facilities. Our finest instrument was their obsolete equipment. The scientists who built the bomb. Meanwhile, Manhattan Project scientists confronted very different questions. They'd succeeded completely. They'd built weapons that destroyed 2 cities and killed over 200,000 people. They'd ended the war. They'd changed warfare forever. Robert Oppenheimer famously quoted the Bhagavad Gita after witnessing the Trinity test. "Now I am become death, the destroyer of worlds." His moral anguish was genuine and profound. Success brought responsibilities German and Japanese scientists never faced because they never succeeded. Many Manhattan Project scientists became advocates for nuclear arms control, having seen what they'd created. Leo Szilard, who'd conceived the nuclear chain reaction concept, petitioned against using atomic bombs on Japan before Hiroshima. His petition failed, but his advocacy for nuclear restraint continued for decades. Enrico Fermi, architect of the first nuclear reactor, later worked on nuclear weapons effects studies that revealed the horrific power of thermonuclear weapons. He opposed development of hydrogen bombs on both moral and strategic grounds, arguing that such weapons exceeded any reasonable military purpose. The Manhattan Project scientists had won the scientific race and immediately questioned whether winning had been wise. German and Japanese scientists had lost and spent decades wondering whether losing had been fortunate. The technical lessons. Post-war technical analysis revealed specific decision points where German and Japanese research diverged from successful paths. The heavy water mistake. German focus on heavy water reactors wasn't wrong theoretically, but it created single-point vulnerability. When Norwegian heavy water production was disrupted, German reactor research stalled. Americans used graphite moderation successfully because they achieved purity levels Germans thought impossible. The enrichment bottleneck. German and Japanese scientists correctly identified uranium enrichment as the critical bottleneck. Their mistake was assuming the bottleneck was insurmountable with 1940s technology. Americans didn't overcome the bottleneck through better science. They brute forced it through massive industrial scale. The plutonium path. Germans never seriously pursued plutonium breeding. They understood the theory, but considered industrial-scale reactors beyond wartime capability. Americans built them anyway, creating an alternative path to weapons materials. The implosion solution. Germans and Japanese assumed weapon designs required gun-type assemblies, bringing subcritical masses together slowly. Americans developed implosion techniques, using high-explosive lenses, creating symmetrical compression. This was engineering innovation, not physics discovery. The computational gap, calculating neutron diffusion, critical masses, and explosive yields required extensive computation. Germans and Japanese used manual calculation. Americans used IBM punch card machines and developed mathematical techniques that foreshadowed modern computational physics. The philosophical divide. At deeper level, Axis and American atomic programs revealed fundamentally different philosophies about science, engineering, and warfare. German science prized theoretical elegance and experimental precision. German physicists sought perfect understanding before implementation. This approach produced Nobel Prizes, but delayed practical applications. Japanese science, influenced by German traditions through pre-war exchanges, followed similar patterns, but with more resource constraints. Japanese scientists understood theory, but couldn't bridge from theory to practice without industrial capacity. American science, particularly American engineering, prioritized practical results over theoretical perfection. If something worked adequately, build it at scale while improving it. If optimal solution was uncertain, build multiple solutions simultaneously. General Groves embodied this philosophy. When scientists told him uranium enrichment might not work efficiently enough, he built 3 different enrichment methods at full scale. When physicists debated plutonium bomb designs, he funded multiple designs simultaneously. When engineers questioned whether implosion lenses could be manufactured precisely enough, he built facilities to manufacture them and improved precision through iteration. This wasn't scientific, it was industrial. It was treating weapons development like Ford treated automobile manufacturing. Standardized processes, mass production, and continuous improvement during production. Professor Hans Bethe, Manhattan Project Theoretical Division leader, later explained, German physics was better science. American physics was better engineering. In warfare, better engineering with adequate science defeats better science with inadequate engineering. We weren't smarter than Heisenberg. We had more resources and better organization. That proved sufficient. The intelligence factor. One element German and Japanese scientists never knew during the war. American intelligence agencies had tracked Axis atomic research throughout the war and concluded early that neither program threatened to produce weapons before war's end. The ALSO's mission, American Scientific Intelligence Operation, specifically targeted German atomic facilities as Allied forces advanced. They captured German scientists, seized research documents, and evaluated German progress. By late 1944, ALSOS reported that German atomic research posed no weapons threat. Similarly, American signals intelligence monitored Japanese atomic research and confirmed it was nowhere near weapons production. Japanese scientists' own reports, intercepted and decoded, revealed their understanding that practical weapons exceeded Japanese capability. This intelligence provided reassurance to Manhattan Project leaders that they weren't in a desperate race. They were in a race where they were the only serious competitor. German and Japanese programs were relevant scientifically, but not militarily. Ironically, American scientists worked with greater urgency than German or Japanese scientists because Americans believed they were racing against competent adversaries. The urgency that came from imagining German atomic weapons ahead of schedule drove American progress, even though German weapons never existed. Fear of losing motivated Americans more than confidence motivated Germans. This psychological factor mattered more than most technical considerations. The final accounting. When complete records emerged decades after the war, the comparative scale of atomic programs revealed staggering disparities. Total investment, Manhattan Project, $2 billion, $30 billion in 2025 dollars. German atomic research, approximately $50 million equivalent. Japanese atomic research, approximately $10 million equivalent. Personnel, Manhattan Project. Peak, 130,000 employees. German atomic research peak, approximately 2,000 scientists and support staff. Japanese atomic research peak, approximately 500 scientists and support staff. Infrastructure, Manhattan Project. 3 major facilities, Oak Ridge, Hanford, Los Alamos, plus dozens of supporting sites. German atomic research, multiple small university and institute laboratories. Japanese atomic research, 2 university laboratories with limited equipment. Production capability, Manhattan Project, weapons-grade uranium and plutonium production, sufficient for multiple bombs by mid-1945. German atomic research, laboratory-scale reactions, no weapons-grade materials. Japanese atomic research, experimental traces of enriched uranium, no production capability. Weapons developed, Manhattan Project, 2 functional bomb types, multiple additional units under production. German atomic research, no weapons, no complete designs. Japanese atomic research, no weapons, no practical designs. The numbers tell the story more clearly than any narrative. American atomic research operated at industrial scales that Axis research never approached. The Manhattan Project wasn't competing against German and Japanese programs. It was operating in a different category entirely. German reactions to scale. When German scientists learned the Manhattan Project's full scale years after the war, their reactions revealed men struggling to comprehend industrial organization they'd never imagined. Heisenberg, in a 1967 interview, stated, "Learning the Manhattan Project's actual scale was more shocking than learning about Hiroshima itself. We knew atomic weapons were theoretically possible. We didn't know Americans would invest billions and employ hundreds of thousands pursuing them. That wasn't a research program. That was industrial mobilization, treating atomic weapons as mass-producible munitions. We never conceived of such an approach because European science doesn't work that way." Otto Hahn reflected, "We discovered fission. We understood the theory. We calculated the requirements. What we couldn't comprehend was that Americans would actually build at those scales during wartime. We assumed the industrial requirements made wartime atomic weapons impossible. Americans assumed nothing was impossible with sufficient resources. They were correct. We were logical. They were practical." Carl Friedrich von Weizsäcker wrote in his memoirs, "The Manhattan Project succeeded because Americans didn't think like scientists. They thought like manufacturers. While we perfected calculations, they built factories. While we debated optimal approaches, they built all approaches simultaneously. While we planned careful research sequences, they threw resources at every possible solution at once. This was scientifically wasteful and strategically brilliant." Japanese reactions to American power. Japanese scientists' reactions focused less on scale. They'd understood from early in research that American industrial superiority was overwhelming, and more on the strategic implications of American willingness to use atomic weapons. Nishina, in post-war testimony, stated, "We knew Americans had industrial capacity to build atomic weapons if they chose to invest sufficiently. What surprised me was that they made that choice while simultaneously fighting wars in Europe and the Pacific. Their ability to pursue atomic weapons as a side project while conducting massive conventional campaigns revealed strategic capability we fundamentally misunderstood." Professor Arakatsu reflected, "Japan couldn't build atomic weapons while fighting America. America built atomic weapons while fighting Japan, Germany, and supporting Allied forces worldwide. This wasn't scientific superiority. This was industrial capacity so vast that they could pursue moonshot scientific projects while conducting global war. We never had chance of competing against such capacity." The Japanese perspective emphasized strategic despair rather than scientific failure. Japanese scientists had understood their limitations. Japanese military leadership had hoped those limitations might somehow be overcome through scientific breakthroughs or divine intervention. Neither occurred. The scientists who survived. German and Japanese scientists who survived the war faced very different post-war trajectories than their American counterparts. Many leading German physicists emigrated to America or Britain, where they contributed to Allied atomic programs.